Welcome to week 3, part 2, in which we're going to return to taking a look at binary search trees. All right, so what we're going to take a look at here is 3 additional operations for binary search trees that we didn't talk about earlier. Back in Programming Prep Day 1, Part 2, 5 years ago probably, we took a look at binary search trees. The idea of a binary search tree is that it's able to store some arbitrary number of values in a sorted order, and typically that's an ascending order. Each of the values in the binary search tree is typically unique, although that's not strictly required. And a binary search tree is implemented as a collection of nodes hooked together with references. Okay? In order for us to be able to construct a sorted binary search tree, we have to have at least a less than comparison between the values. And because of the inherently recursive structure of the binary search tree, where each node has a left and right child, it's very important to be clear about how to use recursion to implement the functions, the methods for a binary search tree. We're going to implement delete, rotate, and balance in this lecture. So I'm not going to repeat all of the detail that we went through back in Programming Prep. If you have lost your recollection of some of that, then I would invite you to rewatch that lecture video. And always remember, as I'm sure you know, that you can increase the playback speed of these videos as long as you can understand more or less what I'm saying. Here we have a representation of a binary search tree of integers. Now, your binary search tree class is going to have a reference called top, referring to the topmost node in the binary search tree. And if there are no nodes in the binary search tree, then top is simply going to refer to none. In this case, top refers to a node containing 12, and underneath 12, we have values less than 12 to 12's left, and values greater than 12 to 12's right. Here is the representation of each node. Each node has 3 components: a value component, and then a left, well, an underscore left component that refers to the next node down in the tree that's less than the current node, and an underscore right component referring to the right side. Okay, so underscore BT node is our internal class that allows us to keep track of the details of individual nodes. And then the binary tree class itself has an initialization method that just sets the tree to be initially empty. All right, so if we create in our program that BT1 is a binary tree, that calls the init function, which sets the top member within the binary search tree to refer to none because there are no nodes in the tree yet. We also walked through the insert method that uses a recursive helper to decide which direction to travel down the tree in order to decide where a new node should go. And if the value that we are inserting into the tree is less than the current node's value, then we head to the left. Otherwise, we head to the right. And again, I'm not going to go through all of this code step by step. If you would like a review, please take a look at the previous video. All right, so we started out with an empty binary tree. If we say insert 12, 12 is now the top node. Whoops, sorry. Too much yellow. All right. Top is now the first node in the tree, and so it goes at the top. and our top instance variable within the binary tree class refers to that first node containing the 12. And then when we insert 7, since 7 is less than 12, 7 gets created and the left child of 12 refers to 7. If we then insert 13, the right child of 12 refers to that node containing 13. And minus 4, well, that's less than 12, so we descend to the left. It's less than 7, so we descend to the left again. And here we've discovered that 7 is not referring to any node on the left, so that tells us where to put that node containing the minus 4. Well, insert is a relatively easy operation because we start with a well-structured binary search tree, and after we've done our insert, we still have a well-structured binary search tree. But delete is equally as important as insert and much harder to implement because deletion can happen anywhere in the tree, and we probably have to do some fiddling around with references to make sure that our binary search tree is still a valid binary search tree after we have done the deletion. So let's see an example here. Okay. So here on slide 12, I have a copy of that binary search tree that we looked at just a few pages ago. I've squeezed it to the left so that we can see what happens after we do a delete. Let's suppose that we ask to delete the 12 from our binary search tree. Well, in this case, 12 is right at the top of the tree. So 3 questions arise right away. What should top be referring to now if 12 is gone? And how do I reconnect the left side and the right side of 12, which is no longer there? You know, there are a whole variety of unsophisticated and sophisticated ways that you can deal with this, but one trivial way, I'm not claiming this is the best possible way, but one trivial way that will work is to move the left side up in place of where the 12 used to be. So we'll have our top node be the 7 in this case, all right? And that's going to entail changing top so that top is no longer referring to the node containing 12 and instead is referring to the node containing the 7. Then what do we do with this right-hand subtree that contained all the values that were greater than 12? Okay, well, this right-hand subtree, since all of its values were greater than 12, they must also be greater than all of the values that are in the left subtree, which is now the top part of the tree. So the simplest, the trivialist thing we can do is to have the rightmost child of the left-hand subtree have the original right-hand subtree to its right. Okay, so we eliminate the reference that we had to the node containing 12. We change top to refer to the node containing 7. And way down at the bottom right corner of the tree starting at 7, that's where we connect our reference to the remaining right-hand part containing all of the values that were greater than 12. All right, and so those values are now all in the correct place because they are all greater than 9 in this particular example. All right, well, what do we do? I mean, this is a straightforward example. I hope it made sense following through that. what do we do if there is not a left subtree? Well, in that case, we can just move the right subtree up and have it become the top, and we're done. What if there is no right subtree? Well, that's even easier. We move the left subtree to the top, and we're done. We don't have to worry about hooking the right subtree onto the bottom right of what used to be the left subtree. Now, we've looked at an example where top was referring to the node that we wanted to delete. But what if we start out with this binary search tree here with 12 at the top, 7, minus 4, and 9 to its left, 13 and 29 to its right. And what if we say we want to delete, instead of the 12, what if we say we don't want to delete the 7 instead? Okay, so 7 is an interior node. Now what do we do? Well, the basic algorithm is still the same. It's just that instead of modifying top to refer to the node containing minus 4, the left child of 7, we're going to modify 12's left instance variable. Sorry, I kept wanting to say component because that's C++ language. All right, so we're going to modify the 12 nodes underscore left instance variable to refer to the minus 4, and we'll hook the 9 onto the lower right side of the tree starting at minus 4. All right, so we do have a distinction between how we handle the top, how we handle it if the node we're trying to delete is at the top, versus how we handle it if the node that we're trying to delete is somewhere in the interior part of the tree. Finally, what can we say about the shape of the tree if we follow this trivial approach? Well, the bad news here is that if we follow this trivial recipe, you'll notice that as we delete more and more nodes, the tree is going to get more and more and more lopsided to the right side. Okay, we used to have a tree that was just 3 levels deep, roughly the same shape at each level. But now, by getting rid of the 12 and following our silly but correct algorithm, our recipe here, now we have 7 at the top. It only has 1 left child, but it's got 3 right children. All right, from the top we go to 7, and then to the right we go to 9, and to the right we go to 13, and to the right we go to 29. So as we continue deleting values in this tree and hooking the leftover right subtree up to the bottom right of what remains, our tree is going to become more and more and more linear, and therefore less and less and less efficient. So that's not a good feature. An important low-level tool that we have for modifying the shape of a binary search tree is called a rotation. And basically what a rotation does is to move a certain node below one of its child nodes. Okay, so we're doing a local change within a tree. We're taking a particular node and we're moving it down either to the left or the right and moving up one of its children in its place. So a left rotation takes the current node and moves it down below, that is, moves it down to the left of its right child, whereas a right rotation does the opposite. It takes a node and pushes it below to the right of the left child. Okay? And so deeper subtrees then have to be reattached in an appropriate way to keep the tree well formed. Here we have an example of a left rotation at the node 12. I'm assuming that my tree is in its original condition when I'm doing this rotation. So if I want to do a left rotation of 12, what that means is that I'm moving 12 down to the left of the 13. So the left child of 13 is going to be the 12. That means 13 itself is going to be the top of the tree. And to the right of the 12, I'm not going to have any right-hand subtree. All right, so I end up changing 3 references. First of all, I change the reference top to refer to 13, which is the new top node. I change 13's left to be the 12. There's the so-called left rotation. I've moved the 12 down to be the left child of the 13. And then 12's right side is now empty. Okay, because if we look at the node 12, all of the values below the 12 are less than the 12, and so they have to remain in the left child of the 12. Whereas, as far as values between 12 and 13, well, there are no values between 12 and 13. 12 and 13 are, consecutive values. Here's a more general picture. Let's suppose that we have a couple of nodes, P and Q, and we have these subtrees, A, B, and C. So A, B, and C are not individual nodes. A, B, and C are entire subtrees hooked to the left or right of these nodes P and Q. We're going to assume that P is less than Q. Therefore, if P and Q are directly connected to each other, then either P is the left child of Q, because P is less than Q, or Q is the right child of P, again, because P is less than Q. All right, so if P and Q are adjacent in the tree, then one of these two situations has to be the case, that either P is the left child of Q, or Q is the right child of P. Now, as far as the subtrees A, B, and C are concerned, well, since A is to the left of P, that means every value in the A subtree has to be less than P. Since C is to the right of Q, that means every value in C has to be greater than Q. All right? And B is the stuff that's in between. All right? So anything in this B subtree is both greater than P and also less than Q. So depending on which of these two nodes, P or Q, is above the other, then P will either have B as its right child, or Q will have B as its left child. In the case where Q is the parent of P and P is on the left side, if I do a so-called right rotation, well, a right rotation of Q means to elevate P above Q. And in order for P to be elevated above Q, that means that Q has to become the right child of P. Well, P used to have B as its right child, so B now has to become the left child of Q in order to remain in the correct position. Okay? On the other hand, going back the other direction, if P is the parent of Q and Q is on the right side, if I do a left rotation, that means to push P down below Q. Q is going to come up and have P as its left child, and the values that were less than Q, the values that were to Q's left, have to be changed to be at P's right. I'm not showing in this diagram, but it's also going to be the case that, there is some node above all this, either top or some higher level node up in the tree, and so that node that's at a higher level in the tree is going to have to be changed. In the case of a right rotation, that node is going to have to be changed to point to P instead of Q. Or in the case of a left rotation, it's going to have to be changed to point to Q instead of P. All right, so there are actually 3 references that have to be changed anytime you do one of these rotations. Okay, so we will be making use of left and right rotations in lots of future work that we do with binary search trees if we want to change the shape of a tree. Next, we're going to take a look at the idea of a balanced binary search tree. We say that a binary search tree is balanced if, and this has to be true at every single node in the tree, not just at the top, the depth of the left-hand subtree is only 1 different at most from the depth of the right-hand subtree. Okay, that is, at every node in the tree, if you compute the depth of that node's left subtree and subtract the depth of the right subtree and take the absolute value, that's got to be either 0 or 1. Okay? Either the depths are identical or they differ by at most 1. Well, either they're identical or they differ by 1. All right? The benefit of a balanced binary search tree, or a nearly balanced binary search tree, is this order log n search time. And as we saw when we implemented our silly rule about how to rebuild the tree when we delete a node, our deletion rule shoves the tree into a linear node on the right side and gets closer and closer to order n performance and further and further away from order log n performance. Here we have some examples of both balanced and unbalanced binary search trees. This little tree is balanced because at node 5, the difference between the depth of the left and right subtrees are, well, the depth of the left is 1, the depth of the right is 0, so the difference is just 1. We also have to check at node 2 the difference of the depth of the left of 2 and the right of 2. Well, those depths are both 0, so those depths are within 1 of each other. Likewise with this just slightly bigger tree, this is balanced because 5's left is 1 deep, 5's right is 2 deep, which only differ by 1. At node 2, the left and right are both 0. At node 8, the left and right are both depth 1. And at nodes 6 and 9, the right and left are both depth 0. So at every single node in the tree here, the depths of the left and right children are within 1 of each other. And then here, for this bigger tree with 18 at the top, this is an example of what's called a complete tree. Different people's terminology differs a little bit. It's also sometimes called a full tree, or some people define those terms a little bit differently, so we could say that this is a complete full tree. Okay, so a full tree, technically, is a tree in which every node has either 0 or 2 children. So this is certainly a full tree. And a complete tree is a tree where all of the nodes are filled in at every level, with possibly just a few nodes missing in the right-hand side of a tree. So if I get rid of these nodes 29 and 37 over here, it would still qualify as a complete tree because there's 1 node at the top level, 2 nodes at the second level, 4 nodes at the third level, and the only missing nodes are down here at the 4th level. And those missing nodes are at the right edge. Anyway, all right, so we'll we'll roll around in binary tree terminology later in FC2 as well. These trees are unbalanced, okay, because 5 has a depth of 2 on its left, but a depth of 0 on its right. Similarly, for this slightly larger tree, we have 5 with a depth of 0 on its left and a depth of 2 on its right. This tree, if you only looked at the top node, you would be tricked into thinking that this was balanced, because 18 has a depth of 3 on the right and a depth of 3 on the... I got my right and left confused. So 18 has a depth of 3 on the left, and it also has a depth of 3 on the right. And so if you only looked at the top node, you would confuse yourself into thinking that this was a balanced tree. All right? The balancing rule is also satisfied throughout the entire left-hand tree. So the subtree starting with 11 is balanced. The subtree starting with 7 is balanced. The subtree starting with 15 is balanced. But when we go over here to the right of the 18, we discover at this node 28 that we no longer have the balance rule satisfied, because 28's left tree has depth 0, whereas its right tree has depth 2. So at the node 28, our balance requirement is not satisfied, and consequently this entire tree is not balanced. All right, so if we find ourselves with an unbalanced tree, which means that it has less than optimal search performance, we can turn that tree into a balanced tree through the application of rotations. And one old and simple algorithm for balancing a tree that's not balanced is called Day's algorithm. Not surprisingly, invented by a fellow named Day at some university in the UK, I've forgotten. And his algorithm basically goes like so. First, we are going to take whatever tree we have and linearize that tree to the right. That is, if we had this little tree 5 with 2 to its left and 3 to its right, we're going to linearize this whole thing into 2 with 3 to the right and 5 to the right. Or if we had this bigger tree here, we're going to linearize that into 1 at the top with 7 to its right, with 8 to the right of the 7, 11 to the right of the 8, 12 to the right of the 11, 15 to the right of the 12, blah, 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 blah. So we turn this thing into just one long, is essentially a list of nodes all down the right-hand side. And this is often called a vine, as opposed to a vine is a subcategory of tree in which all of the values are down either the right side or the left side. In Day's terminology, and I will post the paper that Day wrote from back in the mid-70s, he refers to this vine as the backbone for his algorithm. Okay. Now, sorry. I'll mention that his first step does involve linearizing the tree. He does it in a slightly different way than just using right rotations. But the point is to get a vine, and we can use right rotations to get the vine. So let's do that. All right, so here's a tree, just some tree that I wrote down. It's it's not more or less interesting than other trees. And we see that it's not a vine, okay? The root has 2 children. So we want to change things so that the root only has 1 child on the right. Well, since the root has a child on the left, what we want to do is to use a right rotation to pull that left-hand child up above the 18. And that's going to involve making 18 into the right child of the 11 and taking this subtree that used to be at the right of the 11, that's going to become the left of 18. And then this other subtree over here that was to the right of 18 is going to remain to the right of 18. Okay? So 11 moves up 18 moves down to 11's right. 11's right subtree, which we can think of as being between 11 and 18, now becomes the left subtree underneath 18, and 18 still has its same right subtree. The top node now only has a right child, so we're going to descend to locate a node that has both left and right children. And we come to this node that contains 18 again, and we're going to do another rotation. This time we're going to bring the 15 above the 18. Now the 12 is going to stay to the left of 15, but the 17 here, which is between the 15 and the 18, will become the left child of the 18. So here's what that looks like after that second rotation. 15 is moved up. 15 is to the right of 11. 18 is now to the right of 15. 12 remains at the left of 15. And 17 has been moved down. Instead of being the right of 15, 17 is now the left of 18. Okay, well, we start from the top of our tree again, and we discover, okay, that's only got a right child, so that's good. We come down to the 15. 15 has both left and right children, so we're going to do another rotation. We'll move the 12 above the 15, and the 15 below and to the right of the 12. And that's it. There's nothing to the right of the 12, so there's nothing that we need to reconnect to the left of the 15. And now we've got 3 nodes at the top in a linear sequence. And we'll find 18 again and do a rotation there. And that will bring the 17 up above the 18. The 18 will be below and to the right of the 17. 28 will be below and to the right of the 18. And you can see that at each step we're getting closer and closer to a vine, okay? And I've left a couple of steps out here, but we will get to this vine with 11 at the top and 37 at the bottom, and all of these nodes hooked together in a list on their left sides, on their right sides, pardon me. Okay. All right, so I think I mistakenly said that these were left rotations. Actually, these are right rotations, okay? We're going to use right rotations to turn that original tree into a vine. Now, to create the balanced tree from this vine, now we're going to apply left rotations, but we need to be a little bit more clever about how we apply these left rotations. We're going to apply left rotations on alternating nodes, starting from the top of the vine, or of what Day calls the backbone. And we're going to do repeated passes down this backbone part of the tree until we use up the backbone. Okay? And it will turn out that when we're done, we're going to have a balanced tree. So the rule for keeping track of the length of the backbone is when we get to each pass, we have to subtract 1 from the remaining backbone length. Okay, and the reason for that is to make sure that we don't take our right-hand vine and accidentally push everything over to the left, so that we end up with a left-weighted tree. So we're going to start with our right-weighted vine, and we're going to gradually push more and more of it to the right, but we're not going to overshoot. We want to be careful that we don't overshoot and push too much stuff. Golly, I think I said something wrong. So we're starting out with this right-facing vine, or this right-ordered vine, and we're trying to push things to the left. We want to make sure that we don't overshoot and push too much to the left. All right. So we're going to subtract 1 from the remaining length of our backbone at each iteration of these passes. we're going to start out with our initial backbone length of 1 less than whatever the vine length is. So for this vine, there are 9 values in that vine. We're going to start out with a backbone length of 8. Now, the number of rotations that we're going to do at alternating nodes is going to be, well, if we're going to do alternating nodes, that means every other node. And so it makes sense that we're going to do, whatever the length of the backbone is, we're going to do half that many rotations. And of course, we can't do fractional rotations, so we're going to do a floor divide by 2, so that if the length of the backbone is odd, we won't do half a rotation down at the bottom. Now, we're going to do those M left rotations, stepping down at alternate nodes in the vine. When we're done, we're going to reduce the length of the remaining backbone by the M rotations that we did, and then another -1 to make sure that we don't push things too far to the left. We'll then recompute the number of transformations, the number of rotations that we have to do, and we keep looping through this cycle, computing M, doing that many rotations, subtracting from the remaining backbone length, computing N, etc., until we get to the point where M, the number of rotations, is 0. Sorry, I keep saying transformations because transformation is the terminology that Day uses. Day, in his paper, and you'll see this when you read it, this was sufficiently long ago that I think the concept of rotations wasn't a standard concept. And so he describes a rotation in his paper, but calls it a transformation. Okay, nowadays we call what he's describing a rotation. Okay. Alrighty. So let's walk through this. Here we're going to start with our vine of these 9 nodes that are all down the right side in this sequence. Okay, so our backbone length is going to be 9 minus 1 for our first pass. That is, it's going to be 8 long. That means we're going to do 8 floor divided by 2 equals 4 left rotations, and we do those at alternating nodes. So that means we're going to do a left rotation at 11, then skip a node and do a left rotation at 15, skip a node, do one at 18, skip a node, do one at 29. Now, I say skip a node, but in fact, what's going to happen is that node is going to be readjusted to go above its parent. So when I do the left rotation of 11 and 12, that means that 11 gets moved down and becomes the left child of 12. All right, so we see that here. So 12 is now the parent of 11, and 11 is on the left side. If I then do another rotation, my next rotation is at 15. That means that 15 moves down below the 17, and the 17 has 15 as its left child. So you can see that 11 is moving below 12, 15 is moving below 17, 18 is moving below 28, 29 is moving below 31, and we end up, after our first pass, having our revised tree look like so. Notice that our total length of that right side has been cut roughly in half, but the backbone length, in order to prevent ourselves from going too far to the left, our backbone length decreases even more than that. So our new backbone length is going to be 8, okay, which was the backbone length from what we had before, minus 4, that is minus the number of rotations that we did, minus one more. So now our backbone length is 3. And if we do a floor divide of 3 by 2, we only have one left rotation to perform. So we perform our left rotation up at 12. And this has a really interesting effect because now 12 gets pushed down below 17. This subtree that was between 12 and 17 has to remain between 12 and 17. And in order for that to happen, the 15 has to become the right subtree of 12. Okay, so 7 moves up above 12. 12 moves down to 17's left. 12's left is unchanged. But 12's right now is what used to be the left of 17. So notice that I've gone from having 12 with a 1-node left subtree to now it has a 3-node left subtree. And furthermore, that left subtree is a complete tree. And that's it. I only have one rotation to do, and so now I'm at this stage. And now I calculate my new B length, my new backbone length, and my new M. Well, the backbone length is now the 3 that I had from the previous one, minus 1, the rotation that I did, minus one more is 1, and the floor division of 1 over 2 is 0. So we're done. We have done the number of left rotations that we need to do. And indeed, if we look at our tree, it is a balanced tree. Starting from the node 17, its left-hand depth is 2, and its right-hand depth is 3. Starting from 12, we have 1 and 1. Starting from 28, we have 1 and 2. Starting from 31, we have 1 and 1, and I won't bother counting the 0 and 0 at all the leaf nodes. All right, so that's a pretty simple procedure. Well, at least it's a pretty simple procedure when you draw a picture. It's a little more, it's a little pickier to get done in code, but it's not horrendous. And we have successfully balanced our tree. Okay, so we've taken a look now at what's involved in deleting a node and a naive way of patching the tree back up so that it's still a valid binary search tree. We've taken a look at doing rotations, which make localized changes within a tree to change the shape of the tree. And we've seen how you can use rotations with this thing called Day's algorithm, which is a simple and old algorithm to balance the tree. There are other fancier algorithms for balancing trees, but Day's algorithm is easy to explain. Even better than this is what are called self-balancing binary search trees, which every time you do an insert or a delete will do the minimum number of I say the minimum number of rotations necessary. Actually, it's the minimum number of rotations necessary that's not something that you can kind of mathematically prove. Ideally, we want to do an efficient number of rotations to get our tree pretty close to balanced so that our search efficiency remains order log n. And it turns out there are a variety of different self-balancing binary search trees that have different trade-offs in terms of how much rotating they do in order to get variously close to having a perfectly balanced tree. For example, we've talked about red-black trees, and we've taken a look at the algorithm for balancing a red-black tree after we've done an insert. We haven't talked about deletes, which we would also have to deal with. We will have more to say about balanced binary search trees when we get into C++ in financial computing too.